Here we've got three examples we're going to work through that will utilise that table of derivatives that we've come across, and it's an example showing you how to apply them in each of these cases. So we want to find dy dx. dy dx is the derivative of y with respect to x, or the change of y, instantaneous change of y as x increases. We look at the first one here, and we know we're going to apply the rule if we've got y equals, so if we've got derivative with respect to x of ax to the n equals nax to the n minus 1. So we bring the power out the front, just multiply by the a, and then take one off the power. So that's how we do these ones here. But we've got 16 over x, and we've got the square root of x. So we need to express this these terms in ax to the n. So with this one here, you know if you've got x, and now that's x to the power of 1, you know from your laws of indexes that if you want to bring that x upstairs, you've got to put the negative power. So 16 over x, another way of writing that is 16x to the negative 1. They are exactly the same, just written differently. But that gets it in a form where we can apply this rule from our table of derivatives. Minus, this one is already okay, so we can just put that in there. Plus, now this one here, the square root is a fractional power, so it'll be 5x. Now, because it's a square root, we don't write, if there's a 2 there, we don't tend to write the 2. Just like if we've got 1x, we don't put 1 in front of it, we just put x. But here we've got square root, so we tend not to write that 2 there. But that gives us an indication as to what we put up here as a fraction. It is 1 over 2. If it was the cube root, it'd be 1 over 3. Okay, so we've got each of the three terms now in this form, and it allows us to find dy dx is just the derivative with respect to x of each of the individual bits, terms, not bits, 4x cubed plus d dx of 5x to the half equals. Now we bring the power down the front, so it's negative 1 times 16 x, and take 1 off the power, negative 2. Negative 1, take 1 is negative 2. Minus 3 comes down, 3 times 4x, take 1 off, power of 2, plus a half times 5, so it's a half, 5x. Now a half minus 1 is negative a half, equals negative 16 x to the minus 2 minus 12x squared, plus, now 5 times a half is 5 over 2 x to the minus a half. Probably it's a good idea to, because we haven't got any negative powers in our original question and we've got a radical sign, we haven't got any fractional indices, it's probably a good idea to express this back in that form. So x to the minus 2, if it's upstairs with negative 2, we can go downstairs with positive 2. So it'll be negative 16 over x squared minus 12x squared plus 5 on 2. Now, because it's x to the minus a half upstairs, it can be x to the positive a half downstairs. And if it's x to the positive a half, x to the half is the same as the square root of x. And that's probably the best way of writing it rather than that. However, if you wanted to find out the instantaneous rate of change, you could put in values of x in that and still calculate it, and you'd still get the same answer. But this is probably looking a little bit better. Okay, so let's have a look at this one. We're going to apply our rule, the derivative of e. Derivative with respect to x of e to the ax from our table is ae to the ax. Don't forget to keep the a up there. and the derivative with respect to x of ln x is equal to 1 on x. So we're going to apply both those rules because we've got two very different terms there. So dy dx equals the derivative with respect to x of 7e to the 4x plus the derivative with respect to x of 2 ln x. Now, we could bring that 7 out the front if we wanted to and just go with respect to x of e to the 4x. So let's do that. 7 d dx of e to the 4x, and do the same here, plus 2 d dx of ln x. Now that's probably going to make things a little bit easier for us now, because that's straight application of the table. Derivative with respect to x of e to the 4x, so it's 7 times is 4e to the 4x, that's a times there, plus 2. Derivative with respect to x of ln x is 1 over x, so that's times 1 on x. Probably a better way to write this is multiply the 7 4s, 28, e to the 4x, plus 2 over x. When we multiply 2 times 1, that's like 1. So 2 times 1, 1 times x is on the bottom. That's that one there. So working through that, probably as you get good at these two lines will probably disappear, and many of you will be able to go straight to that line. And you can see that it's just 4 times 7, e to that, and then the 2, and then derivative. So I think after you get the hang of them, I'm just going through them slowly here, but after you get how these work, you'll be virtually go straight from there down to that line and go from there. Okay, so here we've got dy dx. We know derivative. The 3 can come out the front, so 3d dx of cos x minus root 2 d dx of sin x equals derivative of cos is negative sine, so that's negative 3 sin x, and the derivative of sine is cos, so that's minus root 2 cos x. So I've done that one a little bit quicker just to show you. Okay, so that's about as far as we need to go as far as the different types of derivatives we're going to do in this course. The applications of them, I'll do some of those in later videos, but as long as you can remember how to do those, you've got to remember that table of derivatives, and these should be routine for you once you remember those.